Thank you for your patience. And we are now starting next session. I'd like to introduce next speakers. Keiji Shinzato, Young-joo Chung, Phamthanhthao, and Takashi Umeda, Cevahir, and Masahiro Sanjo. They will speak about their research topics. And here is Shinzato-san. Please welcome him. Big applause.
Good afternoon, everyone. My name is Keiji Shinzato from RIT Tokyo. Today, let me talk about my research topic. The title is Extracting Product Information from Unstructured Data. Before moving to my talk, let me announce the wireless internet connection and Twitter. In this room, wireless internet connection are available by setting up this information. And please tweet something you feel into the by this hashtag. Okay. Let's move to my talk. The goal of my work is to develop an automatic methodology for extracting the production information from unstructured text data. The structured data is very useful resources for deploying the user-friendly service like facet navigation here. So as you may know, facet navigation is a very important function for e-commerce site. For example, this is a little bit result of the wine data. So a user can narrow down the list of retrieved wine data according to the wine attributes like wine type, grape variety, country of origin, and winery and others. So this means user can quickly access to the product user want to buy. So in order to realize this function, we need the structured data. So unfortunately, the most of the item in Rakuten Ichiba is not well organized. So that's why I'm working on this topic. Okay. So you may think that the structured data can be easily extracted from this kind of table data in the Rakuten Ichiba. I think this idea is very good. But the ratio of pages, including the table data, is very small. For example, according to our investigation, the ratio of such pages in one category is 38%. So this means the remaining of the page consists of only sentences like this. So we need an automatic methodology for extracting the product information from this kind of text data. Okay. This task has two technical issues. The first is, how do we know attribute of an object? And second is, how do we extract attribute value from an item description? Okay. For solving the first issues, we analyze a large number of table data in the Rakuten Ichiba. And by parsing the table data, we can collect the attribute name for each object. At the same time, by parsing the table data, we can also collect the attribute values of corresponding to attribute names. So here is an example of the extracted attribute value database of wine data. So the first line shows the automatically extracted attribute names for wine, and the other is the attribute values corresponding to the attribute names of the wine genre. So the characteristics of this data is the precision is very high, but the coverage is very low. Okay. So this is a translated result into Japanese. Okay. So for the second issue, we use this automatically created data for extracting the attribute values of the product. At first, we annotate the attribute value information to the actual item page, and then we generate a rule by using the context where attribute value appears for generating this kind of rule. So in this example, at first we annotate Marugo into the actual text data as a region attribute, and then by using words surrounding the Marugo, in this case, the wine from it's used for rule generation. So as a result, so wine from X, then if wine from X, then X is a region. This kind of rule is automatically induced. So this rule is using for extracting the values that are not included in the database. So let me show you some example of the our system. So this is an example of wine category. So the input sentence is an Italian product. So this is a fruity red wine consisting of Sangiovese of the Tuscany. So the system output is like this. The grape type is Sangiovese is a grape type, and Italy and Toscana is a region, and red is a wine color. So this system not only wine. So this is an example of the shoulder bag category. The input sentence is leather and canvas of the back gold. The system output is here. The gold is a bag of color, and canvas and leather is a material bag. And so this framework is not only for Japanese. So this is an example of the French data. So unfortunately, I don't understand this French sentence, but the system understands this sentence and output this structural data. So this is a sentence related to the Super Mario 64. So the output data is product type is Nintendo 64, Nintendo DS, and game title is Mario is maybe wrong, but Super Mario 64 is the correct game title. So this data automatically extracted from this sentence. So let me conclude this talk. So we are developing a technique for extracting the product information extraction from the unstructured text data. The output of the system is very useful for inducing the user-friendly service like fast navigation, recommendation, and others. So this method is independent from any language and any category, as long as the table data is available. That is from me. Thank you.
Thank you for Shinzato-san. And next is Chun-san, please.
Hello, I'm Jung from RIT, and today I'm going to talk about my research on mining, food entity relationship, and recipe service. Let's start. In Rakuten, all services have lots of data, like search log data, and purchase history data, and some reservation data. However, those data are useless unless they are processed, because we don't know what is there. And we RIT analyze this data to produce valuable information. And today I will introduce the new values from Rakuten recipe data. And Rakuten recipe is the service based on the recipes submitted by users. In this service, users can freely submit their recipes by themselves, but that causes lots of writing variations. And let's look at shrimps in Rakuten recipes. Here you have many different shrimps, kind of black tiger is a variety of shrimp, and muki ebi in hiragana, and katakana ebi or kanji characters. And the goal of this research is to find all of these variations refer to the same object, namely shrimp. And how can we use this information that black tiger is a ebi, namely shrimp in Japanese? And if we only use the text similarity to provide relevant ingredient. So when user search ebi, we just return the ingredient that contains string ebi. However, if we know that shrimp, named ebi, can be referred by many different variations, we can return more relevant ingredient to users. Like this, we can show more relevant recipes by this information, which leads to better search experience. But it's very difficult to find such relationship between ingredients, because in many cases there is no text similarity between different variations. Here we have 4 different variations of Abby, but we can't find any common characters here. And Wikipedia doesn't help in this case because the data of Wikipedia is based on the scientific field. When you search black tiger in Wikipedia, Wikipedia shows the result that the formal name of black tiger is ushiebi, in cow shrimp, and we don't use the name ushiebi for cooking. So how can we find that the black tiger is a shrimp? We observed that many users naturally input the main ingredient in the first position of recipe. So as a result, in the recipe in asparagus category, usually asparagus comes in the first position, while other irrelevant ingredients don't come in the first position. So we use the position of the ingredient to find such relationship. So you may ask that, is it true that main ingredient comes the first position? And the answer is yes, and let's look at this figure. The x-axis shows the position of the main ingredient, and y-axis shows the number of recipes. And we found that about 90% of recipes listed their main ingredient in the first position, which confirm our observation. So to find the relationship between different ingredients, we proposed and compared 3 different relevance scores, namely frequency score, TF-IDF score, and first ingredient score. Here we have 4 recipes, and 3 of them belong to shrimp category, and 1 of them belong to crab category. And each recipe contains 3 different ingredients. And frequency score is based on just frequency. Here, shrimp appears 3 times in shrimp category, while just mayonnaise appears 2 times in shrimp category. So we think that shrimp is more relevant to shrimp than mayonnaise. And TF-IDF consider the number of categories. Here, shrimp appears 3 times in shrimp category, while it didn't appear in crab category. So we think that shrimp is more relevant to shrimp than crab. And our proposed approach, first ingredient, is based on the position. So we just give the score to the first ingredient in each category. So here, because shrimp appeared twice in the first position in shrimp category, so we just give 0.2 for shrimp category, for shrimp. An experiment on real data set, namely Rakuten recipe data set, showed that our approach based on the position achieved the highest precision, recall, and overall score, namely X score. And this slide shows the top ingredient with the highest score in shrimp category. And the first column shows the ingredient with the highest frequency score, and next column shows with the highest TF-IDF score, and third column shows highest first ingredient scores. And when we see the first ingredient with the highest frequency score, we can see lots of ingredients such as salt, potato starch, sake, which appears very frequently in all recipes, obtain the highest score. And when we see TF-IDF scores, we can see that there are shrimps in here. However, also the potato starch and ketchup and mayonnaise also obtain the high score. This is because of that many Japanese recipes about shrimp is ebichiri or ebimayo. So this ingredient is frequently appear in shrimp category, but they are not related to shrimp. On the other hand, when we see the ingredient with the high first ingredient scores, we can see there are many variations of shrimp, like yokoebi, black tiger. So it means that our approach based on position work is to find relevance in between different ingredients. So let me summarize this work. And in this research, we try to find relations between ingredients to improve recipe search. For this, we employ the user's behavior that enter the main ingredient in the first position. And experimental results show that we can achieve highest accuracy, and our findings may be used for such improvement. And finally, let me introduce Rakuten data release. We Rakuten provide Rakuten data from various services to researchers freely. It includes Ichiba product data, travel data, and oral facility data, customer reviews, also recipe data. So if you are interested in search Rakuten data Kokai, or just visit this website. And thank you for listening.
Thank you, Shinza. Thao-san, please. Thao-san.
Hello everyone, my name is Thao of RIT and I would like to talk about brand name extraction. My talk will cover 3 points: why brand is important to e-commerce, how brand can be used to lie in Rakuten services, and our approach of automatic brand name extraction. So let's go with why brand is important to e-commerce. It's because a strong brand enables us to consistently sell product. For example, we know that the name of iPhone it has a high reputation. So the name of iPhone has encouraged sales for a series of iPhone, from iPhone 3, 3S, 4S, and now 5. And another one, a strong brand enables us to better match the product with the needs of customer. And relating to this, at Rakuten, we know that Rakuten customer has been paying high awareness on brand by the fact that the top 1,000 queries searched by user include over 30% of brand name. So based on that knowledge, I will show you 2 proposals for how we can use brand in Rakuten to match product with needs of user. First, we can suggest popular brand and product. When a use, for example, when a user is looking for beer, we want to suggest him the top well-known company, beer company like Sapporo, Suntory, Kirin, etc. And together with the popular product of the companies. Or another proposal, we can allow users to navigate through a product lineup of the favorite brand of the user using the landing page when user search for the brand name. When user, for example, when user is a fan of Kirin beer, a product lineup of beer like this of Kirin, I think will definitely satisfy the user. So let me clarify our goals again. So we have tens of millions of product title, and we aim to extract the brand name from the title using an automatic approach. For the example of title of Apple product, we want to extract the name like Apple, iPod, iMac, MacBook as the output for the brand name. And now I will introduce the very basic part of our approach. Point number 1, how did we extract the brand candidate? We need to concern about the word candidate extraction because it isn't like in English. In Japanese, product title usually lack of spaces between words. To give one example, the product title Kirin laga biru kan samikujimiri. How we can make the computer to understand how many words we can find with this. So our idea was to use the search log database because it's based on the knowledge that when user go to Ichiba and he want to find a product, what can he use? He will type the brand name to search for the product. So a simple matching between product title and search log could successfully extract the meaningful word from the title. And with that point number 1, we could extract the word candidate for each company like this. Kirin, Asahi, Sapporo, we have a lot of word candidate. So the next concern that we want to identify the characteristic of brand. And the idea was, we know that every company wants to make their brand name distinct to other company names and product names. And it means that if we put the word candidate of each company into one circle and overlap them together, we can say that the brand name like Kurola Bedo of Sapporo, Kirin Lagarde, Kirin Superdrive Asahi will appear in the very private location. And based on that assumption, we define a statistical scoring function which can well capture the distinction characteristic of brand name. And we use that scoring function to score the word of each company and sort them from high to low score. And we could successfully make the strong name raise to the top. And with that, with the extraction result, we aim to make the current unorganized search result to a system that can best match the user needs. And for the summary, you now know that brands is very important to Rakuten. And brand can be used to encourage sales, which is very important for both merchants and Rakuten itself. And also brands, and as a result, brand can be used to improve the user satisfaction in terms of system G. And our approach of automated brand name extraction was quite effective. Thanks for listening.
Thank you for Phamthanhthao. And next is Umeda-san.
Hi, this is Umeda from Rakuten. Today, I will talk about the purchase prediction by statistical analysis. Prior to main theme, this is about my biography. After joining Rakuten, I've been engaged in the analysis of user behavior and purchase prediction in Rakuten Ichiba, Rakuten Books, and Rakuten Travel, and so on. And today, I will pick up the one example from Rakuten Ichiba. It's about the prediction of user purchase intervals. Here, our objective is to predict the user purchase intervals. In other words, we'd like to predict when user purchase in the next time. It's focused on the consumer non-durable goods, such as pet food, rice, water, and so on. Here is an example of application. For example, this user has purchased rice at about 30 days intervals. And if we can predict this user's purchase intervals precisely like this, we can remind this user just before his next purchase. So if such an application exists, there are many benefits for users. For example, it can prevent many users from forgetting to purchase regular buying items. So here, important question is how can we predict user purchase intervals? So I'm gonna take rice category as an example, and I will pick up the users purchasing rice over 4 times in 1 year as a target users. This is one example of user behavior. This user has purchased rice at about 30 days, so all purchase intervals are fixed. And this type of user accounts for about only 11% of all target users. And it's corresponding to our predictable users. So the coverage of predictable users is too low. So it's not practical for us to make remaining systems. So here we need to expand the coverage of predictable users here more. This is another example of user behavior. This user has purchased rice at 31 days, 60 days, 30 days, and 29 days intervals. And as you can see, most of purchase intervals are fixed. It's closely similar, about 30 days. But a few purchase intervals are outlier intervals. So according to our observation, we found there are a lot of users with many fixed intervals and a few outlier intervals. So we just call those users as a user with a few outlier intervals. And as for outlier intervals, do you know why these outlier intervals happened? One answer is the quantities. This type of user, for example, this user had purchased 5 kg rice at about 30 days intervals. But he sometimes purchased 10 kg rice, and after that, his purchase intervals become 2 times longer. This type of user accounts for about 22% of all target users. This is one answer. And the other example, outlier purchase interval may happen due to some event or user purchasing outside Rakuten. And this is the coverage of users with a few outlier intervals. As you can see, those users account for about 36% of all target users. So in total, predictable users account for about 47% of all target users. So as for half of users, about half of users, we can say we can predict user purchase intervals. And predictable users exist in not only rice category, but also any other categories such as wine, coffee, water, pet food, and so on. And which kinds of items should we show in the remaining systems? As for water category, about 60% of users repeatedly purchase the same item at the same shop. So it means in the remaining system, it's better to show the item which has been purchased before. On the other hand, as for wine category, about 80% of users repeatedly purchase different items. So in the remaining system, it's better to show the various kinds of items every time in the wine category. And this is about summary. We found there are many predictable users in Rakuten Ichiba, so we can remind many users at the right moment. As a result, it can prevent many users from forgetting to purchase regular buying items. And we believe it makes users happy. So purchase prediction will give the benefits for users. And we will continue to work on purchase prediction more in Rakuten. And if you come up with any interesting idea related to the purchase prediction or user behavior analysis, feel free to send a message via Twitter. That's all for me. Thank you.
Good afternoon. My name is Ali. I am going to talk about our work on GPU-based image search. I think most of you know about GPU computing, but I am going to give a brief overview of it. GPUs are basically graphics accelerators, but recently they are being used for as co-processors for massively parallel computing applications. Thanks to the programming APIs developed for them, they can be programmed in high level. They are capable of running hundreds of thousands of threads in parallel. Recent GPUs may achieve more than 3 teraflops performance, and the gap is widening between CPU peak performance. Well, but they are mostly used for scientific applications like simulations, computer vision, data mining, and some applications in databases and cryptography. But there are few applications online because online applications are mostly data intensive, not compute intensive. We have developed an image search engine based on GPUs. Our aim is to search near duplicate images in real time that can be usable in web search. We are looking for example, we are looking for an object that is taken from different angles, lighting conditions, scales. Let's say you have a hardcover book and you are going to search it in the online bookstore. You don't need to write keywords. The only thing you have to do is just take his photo with your mobile device and send it to the server. We have achieved this with GPU support. All steps are implemented on GPUs, and so that faster search is possible with more accuracy. Here is some more details. We have to first build search index. We use local key point descriptors for images. We extract these local key points from images in databases, and all key points are indexed using hierarchical k-means. These are 3 indexes actually, but together with the index we use the key point data also for search. I'm going to talk about it. And this indexing is more than 200 times faster than on GPU than single core CPU. Of course, you can employ more GPUs to make it more faster. That is, we can process larger data in unit time. That means clustering accuracy may be improved. And for unit data size, we can index we can do indexing faster, so that we have shorter index computation cycle. That is, we have fresh index in our data center. Well, in the search step, first, again, key points are extracted from the query images. Then each key point is searched from the index. Then here is our original point. We have a secondary search over key points. Let's say those key points are related with this index, and we do the secondary search to have the even closer key points. This actually improves the accuracy, and it's possible to do it in real time having GPU support. To conclude, we have improved image matching time and with GPUs, and had around 9.5% more accuracy. And it's still hard to handle images with tens of millions, more than tens of millions of images, but open source search engines like Solar can be used together with GPU acceleration for low profile servers. Thank you very much, and if you have any comments, please contact me with my name, my surname at mail.rakuten.com. Thank you very much.
The last is Sanjo-san, please.
Okay, this is the last part of our RIT presentation. I'm Sanjo, a coordinator in RIT. Today's title is Empowering Research Scientists. So it's not research topics. So self-introduction, I joined Rakuten 5 years ago, and I worked as a coordinator for 3 years. I like IT, so I believe IT will change the world simple, innovatively. Today, I aim to let you know our strategy to connect with academia and business. So first, I'd like to share my vision. My vision is innovation. To make innovation happen, I want to change this world by cutting-edge technology, in particular IT. So Rakuten also changes the world so innovatively. So to make innovation happen, our director Masahiro said we need connect. Break down it. We come up with 2 points. Diversity and synergy. So inside Rakuten, we have our organization has diversity and synergy. For diversity, we have 3 research domains: power, intelligence, reality, and also crossing 3 types of roles: scientist, technology, coordinator. And for synergy, there are some research topics, project connecting domains, and we deliver our theoretical technology to service side and value chain. So as you know, we have some members, and each member has some specialty and the talent to expand the R&D. So we need more diversity and synergy. Okay. Don't you take a picture? Okay. On the other hand, outside Rakuten, we have some way to connect academia. For example, connect cooperative research and accessing industry, distributing the data, and make an opportunity like presentation or meeting with business side. Focusing on data, already Johnson mentioned, we have this program, Rakuten Data Releases. We are happy to contribute our data to academia and create a new opportunity for researchers. So if you have any interest, please check this website. This is an example of data, a ton of item data and review data, and from Ichiban, travel, and so on. And not only text, but also images from recipe. Okay, conclusion. We connect academia and business by diversity and synergy model. Inside Rakuten, we need more talent, and outside Rakuten, we want to utilize our data for your researches to improve your researches. So again, we are looking for seeing you again. Okay. Thank you.
Anyone has any question? Please raise your hand.
Please.
So I have a question about the first talk. So you mentioned about the rule extraction from the natural language, but in the extraction process, there might be the learning data. Am I right? I'm very interested in how much data do you need to get a efficient rule from that.
Okay. So I didn't do the experiments for investigating the relation between the data size and the data accuracy. So, but in this case, so we used whole data in one category in Rakuten. So the number of documents is about over the 100,000 pages over. So and I know that so the accuracy is maybe related to this data size of data. So in the one case, the result is relatively high. But on the other hand, the case of the shoulder bag. So in the shoulder bag, we have only the 50 million pages. So in that case, the precision is a little bit smaller than the one case. So I think if we have the over the 100 or so, 100,000 documents or so, the precision is like
100 for the learning data?
Yes. The learning, precisely speaking, the resource of the automatically generating the learning data. So the 100,000 data is very enough for learning the rule.
So I think it's smaller than I expected. Than I thought. So that's smaller than I thought. So I imagine that might be more. All right, thank you.
Regarding the purchase prediction, how did you measure the result of purchase prediction? Did it help the user, or how did you measure the result?
The evaluation of the result, right? Yes. I think it can be evaluated by the test, user test, A/B test, or something like that. And now this is the latest research topic, so it's not conducted in the A/B test, but in the near future, I'd like to conduct the A/B test in the real services.
Okay, thank you.
Yeah, the project prediction, I have two questions. One is that if that prediction technology is, can be applied to non-recurring purchase, like real estate or apartment renting or something. Is that possible? Do you think?
Pardon?
Sorry, can you predict when a person buys a real estate or the apartment or the kind of non-recurring product? Do you think it's possible or can do that?
Non-durable product.
So you're talking about a non-durable product like wine, rice, or but if that's a big product, is that possible?
Yeah, as for real estate, so I doesn't try to the estimate about the real estate, but in case of yes, maybe so real estate is maybe impossible, but some items other than the yes. So maybe it not sorry. As for real estate, it may be impossible, I think, but other items other than rice or water, it's possible, I think.
So how about the purchase with long-term interval, like travel or going to E6 town or something? Is that can be the same as water or rice?
Long term.
With long-term interval purchase with long-term interval. Is that very different from rice or is it?
Yes, that's right. Maybe there are different tendency we can find, I think.
Sorry to interrupt, but houses are too expensive. So how about cars, automobiles? Do you
Yes, yes. So yes. Also, proposed technology, it can possible to the regular buying item or non-durable goods. But as for durable goods, it may be impossible for some category, I think.
But people buy cars every 7 years or so. So
Yes, yes. so that we can get many data, many long data, if possible, I think. Yeah.
thank you.
Okay. About the recipe service.
Yes.
According to your approach,
Yes.
your results should have error in noise.
Yes,
How do you deal with it?
Yes, there are some errors like, for example, many people firstly like the tartudai is or tart category. Actually, it's not ingredient. Tartudai is not ingredient. However, when we find that there are some relationship between the first ingredient and the category, tartudai, or for example, there is some broccoli usually comes first in cauliflower category because many people cook using both broccoli and cauliflower. So we found that there is some relation between the first ingredient. We can use errors as different for different relations.
Thank you. Okay, and then it's time to move on. Thank you for